Like stars. Yes, please.
I don't know. I'm audible to you people. I'm sorry for my voice because of cold and cough. So as you mentioned that I am Jeewan Pandey. So working on similar type of the topic which these people are working on like a star. So if you would like to have to know my email, please put it a small j, cut it @aris.res.in. So by the time we all are well aware of the sun, so no need of to define the sun. I'll go to the class 10th to define the sun. What is the sun? Just a ball in the sky, gas ball in the sky, shining to us, giving the sunlight and all. With these basic parameters: surface temperature, temperature at on the surface of it is around 6,000 degree Kelvin. More precisely, 5772 degree Kelvin, 75772 Kelvin. Mass is 2 into 10 to the power 33 grams. Radius 7 into 10 to the power 10 centimeters. All those numbers you put on the gram and centimeters, no meter, kilometers. Okay. So I'm sorry for that. Everything is a centimeter and these things. If you want to do the kilometers, it's a 10 to the power 5 kilometers, 7 lakh kilometers, then you can say gravity quite high with respect to that of our Earth, 2.74 into 10 to the power 2.74 into 10 to the power 4 centimeter per second square. As you know that it has already crossed half the age, that is a 4.6 billion years. Distance from the Earth, that is 1.5 into 30 centimeters, that we call the 1 AU. I just put it in terms of the parsec. Parsec is a distance that corresponding to 3.26 light year. This is 3.26 AU, yeah, light years. Okay, fine. And the 1 parsec is approximately this 3.1 into 18 centimeters. Why I am doing this so? We just see that sun is very close to us, and all the stars are very far away. Approximately minimum distance of one star, that is closest star, is around 1.3 parsec. Okay, that is around, they are away from 10 to the power 6 times away from us. Okay, so we need to discuss on such kind of the star today. Luminosity that I just mentioned, 4 into 10 to the power 33x, you can say that that is 1 gram of the sun can producing around 2x per second of the energy. Okay, so just telling to you these parameters, just to reminding these parameters, if you forgot since the last 6-7 days, is because of this, to classify the stars which are the sun-like. Just look this figure. Can you remove this one? Yeah, just look this figure. So sorry, because today's Nainital sky is not that much good, so you cannot see the stars in the sky very clearly. Otherwise, you could have seen such a sky from this place. Okay. If so, you will see that you see the different colors of the stars. So what does that mean? The different colors of the stars. That basically tells the different temperature. So how the different temperatures, if the star looks blue, because these are the black body that are emitting on the blue wavelength, looks in the blue. Similarly, sun looks somewhere here at a yellow. And the rest stars, which are having the less temperature than the sun, they are called the red stars. They look the redder. They will peak somewhere here. So you can easily get the temperature from here, right? Wiens displacement law, lambda m into t is equal to constant. So you can get it the temperature from here, from this black body. So these are the different type of star in the sky. So all are they the solar-like stars, sun-like stars? Let us define it. First, I will define the solar twin. I just classified into 3 types: solar twin, solar analog, thank you, and solar type. Solar twin exactly similar to this, like a twins. The temperature is plus minus 10 degree Kelvin. Metallicity plus minus 0.05 dex is a, this is we call the Fe by H. Age has to be the within a 1 giga year, so that you can see exactly what is their evolutionary sequence. And shouldn't have any stellar component, shouldn't be the binary, should be the single star, because majority of the star in the sky are in the form of the binary, more than the 50% of the star. Another one, solar analog, just expand this temperature plus minus 500 Kelvin, then we call it the solar analog. Metallicity in a two factor, let two factor within a sun, that of the sun, whatever the abundances will be there. Again, no close companion. Rest of the star, which have a similar kind of the sun, showing the similar activity by the sun, that we call the solar type stars. To understand them much more better way, what we did is that all the stars, the Hertzsprung and the Russell, what they did is independently they tried to put the temperature versus the luminosity. Luminosity, that is energy emitted per unit time. Okay, that is Ergs per seconds. And the temperature, they plot the temperature versus the luminosity, and they found a fantastic relation here. We just see that. So why the most of the stars are located in that bands, and all the stars in these bands are the solar type or not? Let's see. See the temperature and this luminosity. Forget about the absolute magnitude at the moment. This is the astronomical unit. This is the magnitude, is a logarithmic unit of the this one. That is 10 to the power minus 0.4. M is flux. Flux is equal to 10 to the power minus 0.4 m, where m is absolute magnitude. You call it, just see the temperature and luminosity. Luminosity is nothing but 4 pi r square sigma t to the power 4. Sigma t to the power 4 is Spen's law, right? This is a flux F. If I multiply with the 4 pi r square, the area, then I will get the luminosity. So they follow nicely this relation. You put T and as well as R of them, radius of them, they follow nicely these relations. The sun is located somewhere here in this diagram. This is the sun. This is the luminosity along to the y-axis in terms of solar luminosity. I told the solar luminosity is 4 into 10 to the power 33 Ergs per second in terms of the solar luminosity. And this is the nearest star next to the sun that we call the Proxima Centauri, is somewhere here. The temperature too low. So the star which are nearby, near vicinity of this star, this type of, we call them the solar type of star because they are showing the similar type of the activity by that of the sun. See the point that why these stars which are locating here are not the solar type of the stars. So what makes the stars a solar type of the stars? Here, I'll just come to this diagram again. This is another diagram just to show their according to their sizes. You just go to down the size. Again, this is a Proxima Centauri. Here is the sun. Size of the star will increase from here to here. The radius of the star will increase from this point to this point. Similarly, it evolves. Sun will also evolve at a time. When it evolves, it will leave this main sequence, we call it. It will leave this, it will locate somewhere here. Finally goes and comes somewhere here, goes to right over. So this is just in terms of the another way to represent the HR diagram. So let's see that what makes a star sun-like star. Let's discuss why sun is so special. Okay. So we will just see that everything that is generating the energy is at the core of the sun as well as the core of the star. Sun is as well as a star, right? That you know that sun is a star. Okay, this is a nearby star to us, that's all. So what is the energy transport mechanism which are generating at the core of the sun to the surface? Generally, there are three methods: either conduction, convection, or radiation. Conduction and radiation are the similar process, one by photon, one by particle, right? So which is a more dominant? Because these are the similar process. So which one is a more dominant? Typical energy of the particle is approximately 3/2 kT. That corresponds to the photon energy h nu. Okay. Looks that the number density of the particle is very high inside the sun as well as the star. So it means that conduction has to be the dominant. But that is not the case. Why? We just look into the mean free path. The mean free path of the photon is around 10 to the power minus 2 meter inside this one, whereas it is 10 to the power minus 10 meter. So through the conduction, the energy which is transporting from the center to the surface will take enormous number of the years, billions of the years. The photon will easily carry the energy from core to the center. Okay. So in that way, in case of the star, normal star or the sun, radiation is more dominant than the conduction. But keep in mind, always radiation is not there. Photon can move across the temperature gradient easily, hence major contributor is the major contributor of the energy transport. So this is punchline here. So let comes to the, again, radiation is fine, that we saw that radiation has to be there. Let's look into the convection. Because the method, the transport method of the energy, which is important here, is the convection, which makes sun so special for solar guys as well as for us. If there would have been the convection, nothing will happen there. Only the solar wind will be there, some wind will be there. It will be like a normal star. So what is the convection? It is just mass motion. Occurs when temperature gradient exceeds some critical value. That is, condition of the occurrence of the convection is something like this. I'm not going to derive this relation here. We just assume that it is, the one is a blob, it is adiabatically coming up to the surface from one point to the another point, changing its density and the pressures, and you can get these relations. So that is, this relation has to be followed when there has to be the convection. You can ask the question in between as well. No, it is a dt by dp. Yes, it's a dt by dp only. It has to be some constant as well. It has to be some. This is just to showing that whether it has to be. It has to be. It has to be some constant here as well. It's not clearly as the same things. Okay. So gas is convectively unstable if actual temperature gradient is steeper than the adiabatic temperature gradient. So there are the two conditions that has to be the convective and unstable gas are these two. Either there has to be the large temperature gradient. This can be possible when there is a energy generation is going on. That is, at the core of the star, the energy generation is going on because of the nuclear reactions. So near the core of the star, the convection has to be there. Okay, because dt upon dp is too large. The another condition in the cooler layer of the star, in the outer parts of the star, when you go to the closer to the sun type of the star, sun, gas may be partially ionized. Much heat is used to raise the temperature of the gas. So specific heat at constant volume, that is gamma, the ratio of the specific heat at the constant volume, that is Cp upon Cv, that corresponds to the 1, approximately tends to the 1, not exactly the 1. Such stars have the outer convecting level. That point is clear or not? See, my main aim is that to tell the how the sun is so important and why the stars are so important in that way. There are three methods of the transport: conduction, convection, and radiation. Conduction, we saw that is negligible in case of the star, but it is important in case of when the star is a degenerate. Forget about that at the moment because we are not talking about that. The two methods, convection and radiation. If the star's mass is too high, enormous nuclear reaction is going on at the core. So the convection will be taking place at the core, near the core, in the inner layer of the star. So this is a star which has a mass less than 1.5 solar mass. Because dt upon dp is too large. Okay. Same thing, it's not happening in case of here because dt upon dp you are not getting it here. So in that case, what you are getting is the gamma value, that is specific heat at constant, yani Cp over Cv, is becoming almost 1, giving the steeper temperature gradient here. So the outer layer becomes more convective. So if the convection is here, the third stars are here. These are also the solar type star that we call the red stars. The fully star, there is no radiation. Full star is a convective. As we go from the lesser and lesser temperature, the width that we call convective width, that is going to be increase and increase and increase. Finally, star becomes a fully convective or a small layer of the radiation wave. Okay. So why the convection is important here now? The convection is a mass motion. So if there is a convection, then what will happen? If the mass motion, that is plasma is moving, electrons are moving, whatever are the moving, what will happen? There will be convective eddies, right? If there will be the convective eddies, then there may be generation of magnetic fields. So that's what it makes the important here. So similar thing, whatever is happening in the sun, making the special thing in the sun, because now today you are trying to putting on satellite at L1 orbit, Aditya, because of these things only. Okay. Yeah, in other way around, our survival is because of this only. Otherwise, we won't have been survived here. Okay. Fine. Sorry. Yeah. Is it okay? That is three methods: conduction, convection, and radiation. Conduction is almost negligible in case of the normal stars. Only the two things plays in the role, that is convection and radiation. The stars, I'll come back. The stars above the 1.5 solar mass, the stars from here and above, they have inner convective layer, outer radiative. So convection is not there. The activity which is happening similar in the sun, sunspots, flares, everything, we may not find these things in here. They are free from these things because the radiation is playing the role, dominant radiation mechanism. Okay. So that's what I just said. Are all the stars sun-like stars? Because this is just picture of our galaxy. Sun is located in one arm of the galaxy. So whatever the stars are, they are not. But majority of them. Variety of the stars in the Milky Way, the blue stars which have the radiative envelope are approximately only 4%, and they are very massive stars. Their mass is more than 10 solar mass of the sun. More than 2 solar mass, I would say, the massive stars. Yellow or white star around 7%. White star, I'm including the white dwarf as well. Yeah, that is again different way. This is yellow stars, 7%. White dwarf 9%. Giants. Giants are those stars which are evolved. Evolved means sun has to be evolved in one stage that I will come to when the evolution will be there. Red dwarf, most of they are the populated, 79% of the. Why they are populated much more here? 79%. Why they are long life? See, the star is a massive. So what is happening? The nuclear reaction is happening immediately, very fast. It will explode immediately. So massive star, basically they are following the obesity kind of things. So don't be obesity, don't come has to be this obesity. So the red dwarfs has a 79%, they are the most populous star because they are the long lived in the universe. Their life is too much. So that's the most populous because they are healthy enough, no obesity here. Okay, and distributed all over the sky. Same thing here, I'm telling to you. The solar type of the star are these stars which are located somewhere here in this diagram. So for the astrophysicists, this HR diagram is like your periodic table. Okay. Otherwise, the people, the stars which are similar to here, they follow the similar property of the sun. They are the sun-like star. They are the solar-like, so solar twin. Another two class. Why? So why they are so important? First, I already told that the most populous in the Milky Way, right? Because of their long life, and they form in number of the stars. Other important thing to understand the past and future of the sun. If I take the solar twin, that means plus minus 10 degree, plus minus 10 Kelvin of the temperature of the sun. Then I may be able to understand what is the past because I have a number of the sample of the past as well as the future. So let me put and get the evolution of the sun, how the evolution will happen. So starting with the how they form, how the star forms or how the sun-like stars form or how the sun forms. Usually it is said to be that there is a slow rotating solar nebula. Yeah, in any star, there is a nebula. The nebula has to be disturbed by something. Otherwise, there has to be some perturbations. Otherwise, nothing will happen. If everything is stable, nothing will happen. No? So there has to be some perturbations. If there is some perturbation is either due to the nearby massive star. Nearby, if I am saying the massive star, so massive star has the energy generating at the core is too much. They have enormous radiation pressure. So because of that radiation pressures, the cloud will disturb, nearby cloud will disturb and try to collapse it. Okay. When it tried to collapse it, what will happen? It will try to reduce the size. So the gravity will trying to contract at one point. That is the position is happening. Okay. The inner region of the solar nebula was hot, allowing only the rocky material to condense. The rocky terrestrial planets, this is the planets formed there. The gases and ice regions condensed to cooler outer part, forming the gaseous planet in the outside. Finally, they form a disk around it and form the solar system here. Okay. But in case of the sun, in case of the star or any sun as well, you need to understand how they form. There has to be some molecular cloud. Even if we have seen that now the nice pictures are coming from James Webb. We have seen the nice, these are from the HST, not James Webb. I have to put actually the James Webb. So this is one molecular cloud. So some ionizing source has to be close by it. Ionizing source means I am talking about again the massive star. See, sun has its own wind, solar wind we call it. Massive star has its own stellar wind we call it. Stellar wind is that much of the energetic. It is around 10 to the more than 10 to the about 10 times more energetic than that of the solar wind. So what it will do is that it will disturb it. One thing is this. Other thing, there should have some nearby supernovae. Supernovae means that is blasting of the star. So because of that shocks and all, it will disturb. Once it will palter, it will try to collapse. due to its own gravity. So when it will try to collapse, there is a long story actually. It cannot be done within a few minutes. Like I used to take approximately 20 class lectures of the PhD course of that. So what will happen? It will try to collapse. The molecule will be trying to, it will be, what will happen when it will collapse? There is a conversion of some heat energy. So that heat energy, what it will do? The molecule will be dissociate. Yeah. Anything else? Yeah. Yeah. It will try to sustain now. Now it is not collapsing. It doesn't mean that it's always collapsing. You need to some supporting pressures. The heat is coming now. It is supporting it. When dissociation will happen, again the heat will generate. Again it will have some supporting pressure. This ups and downs will be there. So finally, the temperature reaches to 1,000,000 degree Kelvin. When it reaches to the 1,000,000 degree Kelvin, nucleus will form and nuclear reaction starts. Once the nuclear reaction starts, the energy generation will be from the core, which will be supported by the gravity. Okay. So in that way, it will form the normal star. The sun at the position is a young star. Okay. Similarly, other stars. So gravity wins over the various cloud support mechanism. That's what I am telling to you. Okay. Then triggered by some outer inducing condition that I have already told you. And there has to be some forces that has to be balanced by this gravity. That is basically the heating mechanism, outward pressure. That outer pressure is either because of the dissociation of the molecules into the atoms, because some gravitational energy is converting to the heat energy. Keep in mind only that the potential energy, half of the potential energy converted to the its radiations. Gravitational energy is converted to its radiation. So it supports the clouds at that particular time. So if any cloud in the sky that will collapse, not necessarily. There has to be some conditions that we call the Jeans criteria. So as I told you that this is non-equilibrium condition has to be there to the star formation. The transformation of the gas in low interstellar density, that is initially the cloud density is around, you see the 10 to the minus 23 gram per centimeter cube, and has to go to about 10 to the 22 gram per centimeter. So that much of the transformation of the density is required. So the minimum mass that required, mj, you call the Jeans mass, is something like this. That we can calculate actually. You have some gas pressure, gas energy, and you have some gravitational potential energy that is around 5/3 or 3/5 gm square upon, right? You just compare it, you will get the Jeans mass. So this minimum mass has to be there. You just put these numbers here, and you will get what is should be the minimum mass to form a sun. Okay. So if cloud mass of the cloud is greater than mj, then it will collapse. Even then, after collapsing, how long it will collapse? After the collapsing, there will be the fragmentation as well. Because then this Jeans mass criteria will not follow in certain stage. It will fragment. Again, they will start the collapsing in the different stars. And similarly to the sun. This is the path in the Hertzsprung-Russell diagram, HR diagram, to form the sun. If I'll put the sun in when it was born, the cloud will be located somewhere here. It collapses, the luminosity will decrease. Again, it is sustaining because molecular dissociation happening. It is increasing, luminosity will increasing, and temperature is slightly changing. You just see this is increasing temperature. Finally, when nuclear burning starts, it reaches here. It will be stable stars now. Okay. So how long it will be here? At the moment, all the hydrogen nuclei are fusing to helium nuclei at the core. Once some certain part of hydrogen nuclei will fuse into the helium nuclei, then it will try to blast. So what will happen? There will be no minimum energy, minimum temperature required to generate the to fuse the helium. What is happening actually? There are the hydrogen nuclei. Hydrogen nuclei are converting into the helium. Okay, so you need the higher temperature, right? To do the higher temperature, so sometimes what will happen that we don't have that much of the higher temperature. So what will happen? It will try to collapse. So when it will try to collapse, the its size will decrease and luminosity will decrease. So it will go to the left of this diagram. Okay. When it happens so, when it tries to collapse, again it gets the energy, half of the energy converted to the kinetic energy and increasing the heat. Now it gets the sufficient amount of the helium, sufficient amount of the temperature to fuse the helium, then it will blast. At that time, you may not be no longer here. Yeah, that will take the sun will, it will take the, right. The sun will call to the red giant star. Yeah, this is a diagram that is showing whatever I'm telling to you the story. Okay. I don't know. Yeah, this is expanding photosphere. And the hydrogen core, burning hydrogen core is initially the photosphere here. Later on, contracting inert helium core, hydrogen burning cell. Now, what is happening is that the in that positions, helium is burning on the core, but you have a higher enough temperature on the cells. So, in the cell, because you have a hydrogen, the hydrogen nuclear fusion will be happening there. So, enormous amount of energy generating will expand it. If you compare the sun then and now, it looks like that. Sun as a red giant star. This is assume this is the sun. It is good. Okay. This is the evolutionary path of the sun. That's I was telling to you. What is happening? This left and right always happen. It goes to the slightly left, then right, left, and right, depending on the mass of the star. This is the sun. This path is the sun. Finally, it goes it here. It will evolve and will lose the cell and becomes only the. This is the evolutions. That's what the future of the sun and formation of the sun. I try to finish it off within the time limit to let you convince you that these are the stars, they forms in such a way, and sun forms in such a way. I'll not come to that. This is already I have spoken. Another point that is important, that which I would like to mention it here, is why sun is important. Another one. You just saw that most populous in the Milky Way. To understand the past and future of the sun. Past and the future of the sun is because of this one. You know that we have a variety of, we have the sample now. I have hundreds of the suns. These people have only one sun. Okay. So I have hundreds of the sun. I'll put these hundreds of the sun in the evolutionary track. I will see that what is the past and what can be the future. In that way, we can understand the past and future of the sun. Okay. Then what I am trying to understand it here, the variety of dynamo generated activity. We saw that there is a convection. Convection and the rotation of the star. Yeah, convection and rotation of the sun. They will mix up, form a dynamo, and number of the dynamo generated activity will be there. Let's see this. So what are these number of the dynamo generated activity? So dark spots I saw in the very previous diagrams. There are some few spots on this. You just see that only the 2%, maximum 2% of the solar surface, there are the sunspots. The 2% is making such kind of the problem here, right? Only the 2% of the spots. So a star has up to 50% of its surface is covered by the spots. So what's making is a more up to 50% of this one. What's making it more active? So dark spots that we call the surface inhomogeneity, it doesn't have any dark spots, sorry. Then similarly, we have a spot cycles, similar to 11-year solar cycles. In case of the stars, it's a variety of the solar type of the cycles, starting from a few years, let's say 5 years, up to the 22 years, something like that. You also calculate the surface differential rotation. The point is that how to calculate now the surface differential rotation in the case of the star. You know the sun. You know the sun, the spot is somewhere here and the spot is somewhere here, which spot is moving with speed. I can do that easily, right? And many of lecture you can hearing nowadays of surface differential rotation. In case of the star, how can we do that? That is also one good problem, that it, to just check the surface differential rotation in case of the star. Flares, probably everybody is well aware of the flares here. Star also flares. Then how do I know the star has a flare? I can see the sun as a flare. Okay, some brightening is happening there, then some flare may happen there, some flare is there. Similarly, it has a chromosphere above the photosphere and a coronal emission, that is X-ray emission, because these all stars are the X-ray emitters. Fine. So the point is that I have the sun this closest to this, I can see maximum of the thing what I can do it. And Aditya will do the same thing also. This is the nearest star that to me, Proxima Centauri. I have just a point. Even then you cannot see in the through the naked eye in the sky. This is faint star, very faint star. You cannot see the naked eye. You need a telescope to see it. So I need to do everything, whatever in the sun, in case of the star. So how to probe them in case of the star? This is a satellite image. Of course, this is the sun. I don't know from SDO or where. You just look into this image. This is a 13 days continuous Chandra observations, Chandra satellite observations. You just look into this star. So what did you notice here? The stars, the different stars here, either they are becoming bright and fainter and going to different. Right? Suddenly they becomes brighter and then goes to the we consider that the similar kind of the process is happening here. Why I am considering why the sun is important here now? Because I know the sun, because of the dynamo generated activities in the sun, or there are enormous dynamo generated activity, and this star is the similar to the sun type of the stars. Then if I see the light curve of it, only I can see is the number of photons I can gather it here. I don't have any special information. I can only gather the number of the photons from coming from there. Sometimes they are coming and increasing. I don't know whether I have a light curve of that. So if I'll plot the with time, let's say the flux, whatever the brightness is happening here, it was a constant. Sometimes it goes and becoming constant. It becomes something like that. So I have this behavior only, or something different behaviors when I measure the its light with the time. Okay. So with this, the previous one was in the X-ray observation. This is a with this, then I found that similar to the spots on the surface of the sun. If I rotate the sun something like that, the spot may go behind of that. If it will remain in a one orbital cycle, one rotational cycle, okay, it will go behind. When it will go behind, its intensity will increase. When it will come in front, its entire intensity will decrease. I have that thing only in case of the star. So when the spot will be here, there is a no spot, then light will be high. When the spot is coming into the picture, into the field of view, the light is going to be decreased. When it is exactly in front of you, it's again smaller, and then again going away from us. In case of the stars, They are very fast rotator with respect to the sun. If the star is like a rotator of the sun, like the 27 days, it may not have that much of the spot. Everything depends on the rotational velocity of the star. It may have this, but you are unable to deduct it. 2% of the light dimming cannot be deducted by the telescope here. May be deducted, but may not be deducted. Okay. So that means if you see that, we have approximately 5 to 35 to 50% of the star surface is covered by such kind of the spots. Why there are the spots, I am not going to teach here. You have already gone through this since last many lectures. There are the spots in the sun that you know, right? And why they are? That also you know, okay. That also. I told you that stars which are similar to them are the sun-like stars. Of course, similar fashion, similar mechanism will happen in case of the star as well. So they may have also the spot on the surface. So how do I identify these are the spots? Is this way. But one may say that the variation may not be because of the spots, right? Maybe something else is there. So how to establish it? If you see the sun, the spots may not remain stationary. The spots may not be there. In one cycle or two cycles, they may go away, even in one cycle as well. So what will you see that? You will see that we'll observe this in the for number of the cycles. After the number of the cycles, sometimes this will become the straight when there will be no spot. Spot size will be changing actually. The 2% I am telling in case of the sun is a maximum, right? It's a maximum spot coverage of the sun. So if I will change the size, similarly the depth of this light curve will change. In that way, I will establish, okay, there is a some spot kind of the thing. So I need to find out the size, everything. So that goes on the simulation now. Not going to that. Yeah, these are the things whatever I've talked already. Observe stars continuously, change in brightness indicative of the spot size is changing. Change in shape of the light curve, spot shape is changing. Change in color, that is the temperature is changing. Usually shows two dips in the light curve generally. It has a two spots always. Okay. Yeah. Even if you see that this is one cycle to another cycle, it's not exactly same. It's a changing the cycle. This is a continuous observation by the Kepler satellite. Kepler was a satellite looking continuously in a single field of view for 3 to 4 years. So this is 2080, around 40 days cycle. You just see that all these things are. Now, top of that, what you are looking at here is there is sudden brightness increasing here. The regular variation is there because of the dark spots on the stars. The sudden increase of the light is also seen. So why the sudden increase? Microlensing, if there had been the microlensing, there has to be some object in front of it because these are the close bys. The few parsec distance objects are there, right? Some similar kind of things. If you see the carefully the light curve here, then you found that there is a sudden increase and exponential decay, which usually follow the burst light curve, burst model. That is sudden enhance exponential decay, similar to the solar flare kind of. These are also the solar flares, similar to the stellar flare. So I need to understand if there is a stellar flare, solar flare. So solar, in case of the solar flare, you can at least loop length, you can derive it. Manually, you can see that up to which height the loop is gone. In that case, I also need to do that. So Aditya will be helping in that way. Okay, we have some solar flares. It will be monitoring continuously. Let's generate a model for that in case of the sun and apply to the star. Only the issue comes when, because these are the highly active, sun is a very less active star. Okay, whether these are applicable or not, the physical conditions are applicable or not, that has to be validated. Yeah. See, I just saw it here just to explain you the single spot. If there are two spots, they are usually 180-degree apart. So then what will happen? There will have two dips. And some dips may be here. Okay, sorry. Okay, because there are two dark spots. Okay, one dark spot is here, the another is coming here, something like that. So two dark spots will giving the two dips in the stellar. They are depending on number of the spots. Generally, it was found in case of the star there are major two dips, and small dips may be there. This may be not. This may not be noticeable. Yeah. The same thing that is a real light curves that I want to tell you that. Just I saw that this is just to showing the simulation, and this is the real light curve, and happening where the spots are there and where the flares are happening. Yeah, these are the flares where the regular variation is because of the dark spots. Apart from the regular variation, you can just see the spikes here. Small spikes. While zoom in the spikes, this is the regular variation by this, shown by this. And top of that, there are the spikes. These spikes are small flares on the surface of the stars. And this is a flare that is observed by the Indian satellite AstroSat in one of the active star. Yeah. Then long-term variation, as I told you that sun has a long-term variation. You just see that the images of the sun along the 11 years. But if I will take the image, I may not find any difference in case of the star. Ultimately, I have to take the photons. Okay. So if I plot the photons here, this is the one very active star that we call the AB Doradus. It's the southern hemisphere stars. We just see that the long-term variation. These are the small variations. You just see that these small variations are here. This is the long-term variations. So this long-term variation, if it's 1980 and 2000, approximately, it comes to 17 years. It appears that because we don't have the observations more than that, I have this observation, it is coming to be somewhat, again, increasing it. So it has a long-term observation showing the similar to the solar type of the cycles, 17 years. Apart from that, there are many other cycles. This is the core science again. So when you will enter on the core science, then you will be able to understand all these things. Finally, I'll come to the point why everything is so important for us. In case of the stars, this is important. This is X-ray luminosity versus the bolometric luminosity. Upon the bolometric luminosity, X-ray luminosity is the luminosity in the X-ray band, that is 0.2 to 10 keV energy band. Bolometric luminosity, the luminosity in entire electromagnetic wave band. That is the fraction of the X-ray luminosity in terms of the bolometric entire luminosity. Okay. Why X-ray luminosity is so important? Because if any star is active, definitely it will be the X-ray emitter. For example, the star which doesn't have the convective envelope is not X-ray active. It's not active star. It doesn't emit the X-ray. Okay, this is one of the criteria that if any star you will find it out in the sky is emitting the X-ray. First criteria is just to check whether it's a solar type or not. So what I did is that here, this is a period. Period means the rotational period. Okay, the rotational period versus the X-ray luminosity. We just see that this is the location of the star, sun. Just find that what is the Lx upon bole. That is only 10 to the power minus 6 of Lx upon bole is of that of sun. And rest of the star, you just see that these are here. Way above the sun. They are so active. Even if I'll do that, if you see that, because there are some this plus and are some upper limits and all, forget about that. If you see that they are following the linear relation, then constant, then again decreasing. As star becomes more faster and faster, it becomes more active and active. Means active and means like a similar solar kind of activity, star kind of activity is increasing. I mean, if I'll rotate the sun more faster and faster and faster, its activity will increase and increase and increase, and it will reach somewhere here. You call it the saturation regime. So why the saturation? They are saturated, no more activity will happen there. Some has to be saturated. Then again, they are going to be decreased here. That we call the supersaturation region. There are many reasons for the saturation and supersaturation regions. The corona is very stratified. Many other reasons, I'm not going to tell it here, but this is still a problem. When we rotate the star faster and faster, its activity will increase, it will be more active, and this activity directly depends whether there is a habitable zone or not. Right? If the star is too active, giving the too much of the X-ray, will you survive here? Can't. Okay. There has to be something. So the people's nowadays is to understand how the activity affects on the planet formation, on the planets. Okay. So finally, so what Aditya can help us? There are 7 instruments that, as far as I know, 7, right? 7 instruments. And 4 of them I mentioned it here, but I can understand that is one is important one is visible emission line coronagraph, VELC. What VELC is doing is still you don't know what is the origin of the coronal mass ejections. It will help to understand what is the origin of the coronal mass ejections. Currently, you are also probing the CMEs in case of the stars. So what we have the CME in case of the star, only what I can see is that after the flare or during the flare, some additional material is coming towards me. Because if I'll model it, I need some additional material to model my spectrum. So that's what I have only. So in case if you do that, you will make some scaling laws in case of the sun, will apply to the star, then will help us what is the exact region. Okay. Again, the suit to measure sparsely resolved solar photosphere and the chromosphere will help us to understand exactly what is happening there. That things will be applicable to this in case of the stars. Everything is because of the proximity of the sun. You can see everything in case of the sun. Everything means whatever is our limitations. We will apply these things to the stars. These 2 instruments showing the low and high resolution spectroscopy will always be good in case of the stars. Let's model the sun with respect to them and apply, because what I have to do is that in case here, I'm just assuming the sun is a star. You just take the entire light because I'm getting the entire light from the stars. I have to do the reverse way. These people will probe the everything. One has to do that in the reverse way. I've just assumed this is a single point star is located at a few parsec distance. Okay. So in that way, you will see that what is happening, whether it's applicable to the similar things in case of the my star or not. Let's apply it to the stars. If it is so, in that way, the Aditya will help. I think that's all. Thank you. You can shoot me now.
So, questions?
Yeah.
So you told us the different number percentages of stars, and that you didn't include the yellow and white star in the solar type stars. I'd like to know why, because our sun in itself is a yellow light star.
I don't know. Okay, fine. I just included the red and yellow stars.
Uh,
Can you go this diagram? ये इस वाले में चले जाओगे? Yeah, fine. Yellow star means the star close to here. Red star means that's what I defined the stars solar twin. Solar twin means exactly here. Sun-like means close to here, and rest of them are the solar type. So that's what I haven't included it here. Red dwarfs means these are the stars. These are the red dwarfs. We call them the M dwarf. We just look into them. This
Yes, sir.
O, B, A, F, G, K, M.
Mm.
It's a different spectral type. This G is just G2 is the sun's spectral type.
Yes, sir.
Okay. So that's what I haven't included, because solar type, sun type stars are this, and red type stars are more populous in the sky. M dwarf stars are more populous. And there are some stars which didn't become the stars. Yeah.
So the sun is in the main sequence phase.
Yeah.
Ultimately, it will evolve and it will reach to the red giant phase. But in the red giant phase, its size will be increased.
Yes.
So why is it so? Why the size will increase?
See, what is happening that I told you that probably you missed it. Initially, what is happening? Hydrogen burning is there. Okay. So later on, it will sink and start with the helium burning. When the helium burning starts, enormous amount of energy will be generating. Is not the gravity is not sustaining that in radiation pressure. So what will happen? It will try to expand. That's what. Yeah.
So, how do we predict that this sun-like stars will enter the main sequence turn-off point, or continue over the evolution, or enter a blue straggler star phase?
They will not go to the I don't know. They will go to the blue straggler star or not, because the A-type star they goes to the turn-off point. But everything they will. I'll come to the next one. I'll just show it. Yeah. You just see the evolutionary sequence. This is for the sun. This is for 1.25. This is also sun-like star. This is for the M dot directly goes to up. When you go up, you just see that the left side is over. Yeah. Yeah.
Like, what properties do we exactly use to get the evolutionary path?
What properties? Basically temperature and luminosity.
Okay. So
See, what we have to do is that for that, what people do is that they study the star clusters. The star clusters have a variety of the stars. They have a different age of the star with the different spectral types, a different temperature of star. Then they see that how they are evolving. Now, after that, then what we have is that theoretically you can predict the isochrones. Isochrones means that is depending on the age, different age of. In that way, we can assume, we can consider that what is the age of its age and what's other's age. Basically, temperature is changing, luminosity is changing. Even if sun will go to the red giant star, its luminosity will change. Enormous, it will be quite big, but the temperature will be decreased, right?
Sir, in the HR diagram, like why there are like most number of stars lie in that region? Is it because they are like long lived and that's why it's
They are long lived because of that's why they are lying in that region.
okay? And you said about genes and stability criteria. So can you like explain briefly about that?
Gene stability criteria is that it has a minimum mass to collapse the star. If the mass is less than this, equal to this, if the mass of the cloud, there is a cloud. The cloud mass has a minimum mass that corresponds to the gene's mass. If mass is more than that, it will try to collapse. Otherwise, not. It will remain all distance.
And sir, what is Chandrasekhar limit?
It's forming of the white dwarf, 1.44 solar mass.
Okay.
Yeah.
And one more question. What is the role of neutrinos in supernova explosion?
Role of neutrinos in supernova explosion, I cannot correctly answer it, but it's after the supernova explosion, what I feel. It's not before this one. Yeah.
It's not the topic. Yeah, it's just
Even if not the topic, but it's fine. You can discuss it. When there are supernova people, then you can discuss them.
Thank you, sir.
Yeah, stellar winds are much more powerful than solar winds.
Large mass leads to much more activity within them or something else.
Yes, because of their large mass.
That is it.
Yes, of course. Not stellar, for example, the stars similar to the sun have a similar type of the solar wind. The stars, I don't know. I'll come back. Yeah. The stars which have a similar type, that is the solar wind, the star which the stellar wind here is less than that of the sun. Star here is more solar wind here. Solar wind depends on the radiation pressure actually. So when the radiation pressure is high from the core, it will eject the more mass from the surface of the star, resulting to higher stellar wind, strong stellar wind. Okay, the mass is lesser here, so stellar wind is smaller than that of the sun.
Sir, this speaking about solar cycle, we have seen that it depends on meridional flow, right? So we have like 11 years. What that can be said about other stars, like, and what does it say about their activities? Like just example that you showed, it has 17-year cycle. Are they more violent type of star, depending on what?
Yeah, depending, that is also the important point to do the research as well. People have tried to do that rotation versus these cycles. They didn't find any correlations. This is stochastic at the moment. So if you have a more sample, then you are able to say that what is the exact regions. If there is any relation between the rotational period as well as this one, the long-term solar of the cycles. Even if we saw that the cycles with the around 20-30 days period of the stars have a cycles less 5 years and so. But they are the evolved stars, but there is no one-to-one relations in case of the sun and stars. It's still yet to probe.
Thank you.
I don't know if anybody has did it, but yeah, that's what I'm saying to you. It depends. It doesn't depend on the. That's what I'm saying to you. Not only the mass, it depends on actually the rotation period, because rotation makes the more active or not active.
Should be more of rotation period.
Yeah.
Mass. Because mass will determine surface temperature, but then rotation period will determine how your activity is evolve. Depending more on
That there is though yet there is no one-to-one relation yet. Not.
Sir, like in this sun formation or like star formation slide, you mentioned that the cloud basically set us into a disc-like structure. So why does it exactly set us into a disc-like structure and not some other structure?
See, what they are trying to start is not trying to rotate it. Okay, why they are trying to rotate to make the to conserve the angular momentum.
Yeah. So but why not some other shape?
So
Like, why does it have
momentum will be conserved by this way only? This is the optimum way. Optimum way to conserve. Other shape is spherical shape cannot be there. No?
But then again, they like everyone can rotate in this like similar plane, but of course some will rotate in this, some will rotate below it. Like a spherical shape might also be possible, right?
No, because at the same time, not only this disc shape, because even in the planar formation is because of the disc shape only, right? Yeah, spherical shape cannot form the planets. Okay, disc shape is because of that. What I understood is that because of to conserve the things, conserve the angular momentum. Yeah.
Yes, sir. Yes, sir, I will.
Yeah, you just
But again, like
Uh,
even if it is a sphere, like I'm just going by the conservation of angular momentum argument. Even if it is a sphere, let's say that let's say because even then the particles are just like moving in the
In the
like
s-
angular momentum is similar, right? It is just that they are not in the plane anymore. They are just in different plane.
in case of the sphere,
Yes, sir. In case of the sphere,
right?
so now I conserve angular momentum is still conserved. Like
If the disc-like structure will be not there, let's assume the spherical structure, right? You say that. If I will not conserve the momentum, let's say that if I'll conserve the momentum in both
Yeah.
cases, I don't know exactly, but it forms the disc-like structure. That's what the study is there. And to convey the
that is the question. Like the even accretion discs are formed in a disc-like structure,
Right,
but
right.
not a spherical structure.
Yeah.
So that is what I want to like know. Why the
Yeah,
conservation of
that's
angular momentum does not guarantee that it has to be a thin disc only.
agreed on, partly agreed on. It doesn't have a thin disk. It may, you are mentioning is that if this is a point, if this is here or here, but wherever the point is, this is moving it.
Yes, sir.
Momentum is conserving.
Mm.
I don't know exactly. I need to check it.
Then yes, sir. Then let me know. Yeah,
But it has to be basically. It has to set that. It has to be the.
that is observational fact, no doubt.
Yeah.
Hello, sir.
Yeah.
Sir, so what will be the core and the envelope in the variable stars? And what is the reason behind the variability?
What will be the core?
What will be the core and envelope in the
Or
structure?
that depends. Actually, variable star. Actually, there is a Jew of the variable stars. Why the variability is there? Even the variability is because of the pulsation as well. But whatever the variability talking about it here, the envelope is always the convective. See, what I'm saying is that the faster the rotations, the dynamo will be generate much more. The dynamo activity will be much more. Hence, the activity related dynamo related activity will be much more. So activity will be more. That means if the activity is of course more, then it will produce more X-ray definitely, because X-ray is getting of the basically coronal heating and all. Okay, so if activity is more, that's it is getting the more.
You have
more
seen
X-ray.
in one of the plots shown by Flickr X-ray plot during solar activity cycle.
Yeah,
During maximum
and when minimum, you just see
the
that
level of solar X-ray flux has increased during maximum, if you have seen. So the overall X-ray flux will increase because the temperature of corona will also be higher.
Higher.
So the overall.
Right. Yes, increases the temperature of the corona, just increasing the X-ray. Basically, X-ray is that's the Bremsstrahlung origin, right?
So,
Yeah.
okay.
Ah.
So you showed us a light curve that was periodically varying. What was that variation of, I mean, how was that variation coming up? The periodic one. This one, yeah. What did you say these variations were because periodic variation?
The periodic variations is basically, I just told you that's the previous slide.
No,
Dark
okay.
spots on the surface. Okay.
So, but as you already, I think there was some discussion about the variation, the cause of the variation, that pulsations could also be a cause. So if let's say I have a light curve and I want to understand the variation due to sunspots versus the variation due to pulsation, how would I differentiate between
I
it?
told you that I need to observe this star continuously.
Hmm.
So if variation is due to the spots, you just look into that. The light curve shape is not similar from one to another light curve. Shape of the light curve is changing. You just see that. One is here, some different. Then again, we just look at it and look at it. This is the one cycle from here to here.
Okay.
The another cycle becomes different. Another cycle is different. The cyclic variations, one from one cycle to another cycles, it is changing. The shape of the light curve is changing. For example, in one cycle, the light curve will be something like this.
Mhm.
The another cycle, the light curve will be something like this. There will be the shift of this minimum. Like this is one light curve, this will shift, something like this will shift. It will shift as which. Why it is shifting? This minimum is shifting. This exactly, it may not be exactly of the same time of it one rotation cycle. Why it is shifting? Because of the spot on the surface is moving.
Okay.
So because of it is moving, this is also shifting. In that way, I can establish that this is because of the dark spots. Pulsation, if there is a pulsation, always give the constant sine wave.
Okay.
Okay. Not a deteriorated light curve like this. Yes.
More questions?
Sir, why are white dwarfs hotter?
Why are white
White
dwarfs
dwarfs
are hotter? See what is happening when this evolution of the star is going on. When forming the before the forming on the white dwarf, there will be a red giant star. So the nuclear burning started very highly there. Now it's not hydrogen, now helium burning started. So if helium burning is there, the temperature will be very high. The outer envelope will be go away, white dwarf will be very small. So its luminosity will be very low, but temperature will be very high.
Okay, more questions?
Sir, in our real life, if we see the stove, if it high temperature, it is in blue color, then the temperature decreases, it looks brighter. But in higher, even in higher temperature, there is some higher magnitude there for some stars. Why?
Higher temperature, higher magnitude is fine.
How?
It's not only depending on the temperature. See, temperature difference F is equal to sigma T to the power 4. Right? Then if I want to calculate the brightness, luminosity, then L is equal to 4 pi d square sigma T to the power 4. You have to multiply it by this. So it depends as well as the radius of the star. The blue, the star, for example, here. Oh, yeah. Yeah. Blue, the star, they are bigger stars. Their size is as well more. That's what they are. Blue as well as size is more, their luminosity is also high. Both, not only the T, but R is also high. Radius is also high. That's why they are brighter.
Okay, more questions?
Sir, you spoke about the differential rotation in the surface of this kind of sun-like stars. So I was curious to know that through the light curves, how are you distinguishing the differential rotation and everything?
The two way we can distinguish. One thing is I'm just telling to you that the shape of the curve. The light curve, it is shifting actually. Another way is doing the periodogram analysis, Fourier transform, FFT. If you have the continuous data nowadays, like giving the Kepler as well as the test, you can do the FFT, you can see the different peaks in the FFT. So you'll have a two different period at two different times.
Yeah, but will that be latitudinal information in that?
No.
Yeah,
It's
so
a 1D now. Can't do the latitudinal information.
okay, so the differential rotation will be
We
giving the
say that
information
there
on
is a
the...
yeah, we say that there is a differential rotations. So what you do is that basically light curves. The light curve information at least tell you that there is something differential rotation, but at which latitude? It's a very tough. So for that, what we need to do that you have to do some spectroscopic analysis. Optical spectroscopy. You do that. You just have a lines. You just read the lines. When there is a spot, the line has some bump, dark spot, temperature is less. If it is a white spot, it is a dip. That we call the Doppler imaging. So through the Doppler imaging, we can at least constrain the location of the spot on the star, latitudinal location.
Okay, so these kind of work in this the latitudinal location is in a error. Acha, not
Rather tough. You can say some. We can constrain actually. If you know the log, if you know the angle of inclination where it is rotating, so you can see that this part is always visible. This part is not visible. So through the 1D light curves, you can see that okay, between this to this, the spots may be there because you are getting the modulation from here. So this, let's say minus 45 plus 45. So that big range you can see. Can't see. It's always will pose problem that we have already published the paper with the group with as well, but always will pose problem.
Okay.
Not possible.
Yeah, but can you like cross correlate with the periods that we have obtained for the sun at different latitudinal bands to see which period matches or something?
That can be done. I need a manpower. That can be done. Even then, I'm trying to take entire solar flux, take the entire solar flux, just image it and find out what is the light curve will come out. So that they can do that. So Group did something about these things. He just also took some entire solar flux and did it, but not succeed yet.
Okay. Nice. Thank you.
Okay, more questions?
Yeah. Want to ask something? Very tough. I haven't seen any paper. It's a very compact. It's a compact object. Its compactness is too high. The good ideas, differential rotation neutron star.
So I have a question myself. Since this is a special lecture, I'll ask. So the solar flares, when we observe, so the spots we observe in white light, and then the flares we won't observe, we see X-rays in another wavelength. But then you seem to have shown light curves where you show the spots as well as the flares together.
Yeah.
What is the difference here? Can you tell me?
Yeah. Like this one.
Yes. So this is white light, or
this is white light.
This is white light,
This is
and
white
you
light.
still see the flares. Some of the solar flares are also visible in white light.
Only what is happening is basically the brightness is increasing here.
Yes.
I am not getting the brightness.
Yes.
If I zoom it, I'll see the burst light curve.
Yes.
This flare light curve here. Second thing that if I want to study, because what I want to study is that whether this flaring happening when the spot is close by or not.
Yes.
That relation is not yet.
Yeah, but I presume that you observe, if you look at X-ray light curves, you will see more flares.
Oh yeah.
Right.
Oh yeah.
Yes.
Because it goes to the X-ray, no? This is the X-ray one.
Yes.
This is the X-ray one.
So one more question I have regarding that the spot shadows.
Yeah.
With respect to the if you see the light curve, no, even before the model where you show, yes. So unless you resolve the star, so if you don't resolve the star, then my brightness, integrated by brightness here, and here should be same, right? So why do you then see a dip? Unless either you should suddenly see a dip, or as soon as it arrives there, you should suddenly see a dip and then flat, and then suddenly you should see increase.
For
right?
example, if it is a 27 days of the period, let's say, I have to observe it continuously 27 days.
Yes.
So let's say on the very first day, I don't see any dip. Continuously, I'll plot for the 27 day. Then when the spots is coming to field of view of mine, that light will be going to down. It's continuously going down, and if going away, then it will go away. Even then, if during this period the spot will vanish, then suddenly light will come up.
Okay. More questions? If not, let's thank Jeewan again. Thank you very much, Professor Jeewan. So we now break for tea, and after that you can continue the projects. So yeah.
मैं इसको ले लूं? Yeah.
We get the light of interest. So there is a diagram